Right, guys, I apologize for not being there in person, but I hope these recorded lectures will sort of substitute for me in some way. So this lecture is on what is called the bisection method for solving nonlinear equations. All right, so what are we trying to do here? We are given a nonlinear function, and we're trying to find out where this function intersects the x-axis. In other words, what is the function, what is the value f of x where, what is the value x where f of x is equal to 0? This is what we're trying to find in this method. All right, so we've seen problems like this before. In the last class, I set up a problem for you where, for example, you were trying to fire a cannon. This was your cannon, my poor impression of a cannon, and you're trying to fire a shell, and you wanted to land distance d away. And I gave you the equations for doing this. If I were to just stop at this point and ask you how you would do this, I suspect you might come up with some kind of a predictor-corrector algorithm, okay? So what you might do is to point the cannon a certain direction, fire, and you probably overshoot or undershoot your target, okay? Well, if you overshoot your target, you would probably correct. You would probably lower your cannon and fire in this direction. And let's say you undershot your target. What would you likely do? You would probably take these two angles, and you would probably take some angle in the middle of these two angles and then fire the cannon at that particular angle. And you keep doing that until you hit where it is that you're trying to hit. For me, this reminds me of Angry Birds a lot. Now, I don't know how many of you played Angry Birds, but this is sort of how I play Angry Birds. All right, so the bisection method is almost exactly this. Okay, it's just a mathematical formulation of what we've done right here. All right, so let's start with some basics. So the bisection method is based on something called an intermediate value theorem. Okay, so let me give you an intuitive feel for this theorem, and then I will give you a mathematical statement of this theorem. So the theorem goes something like this. So let's say you have a function. Let's say it goes like this. And let's say you have two values, x equals a and x equals b. So I'm interested in this function over the interval a to b. Okay? So clearly at this particular value of x, you have the function value fa. At x equals b, you have the function value fb. Okay? So now, if I were to pick a certain value y in this range, okay, let's say I pick y right here somewhere. Okay, so y is here. All the intermediate value theorem says is that if I were to pick a value of y between fa and fb, then there must be a value of x between a and b such that f of x equals y. Okay, so once again, I give you an interval a, b, and then I'm looking at fa and fb, and all the intermediate value theorem says is that if I were to pick a y in the middle of fa and fb, then there must exist an x such that fx equals y. Okay, so formally stated, given x in a, b, and y in fa, fb, then there exists a value x such that f of x equals y. I should say given interval Okay, so you have an interval you have a function f defined over this interval ab, and I've given you a value y, which lies between fa and fb. Then there exists a value x such that fx equals y. I've made an assumption here. I've assumed that function f is continuous over the interval. Okay, so nothing deep here. I'm not going to prove this, but this is a relatively simple proof. All right. So if I were to stop at this point and say, how do you use this intermediate value theorem to solve for fx equals 0? And if I were to give you a minute, you would probably come up with this hypothesis that if I were to have an interval such that this is A, just say A, and this is B. Okay? So what I've done is I've taken two values. This is FA and this is FB. Okay? And notice that the sign of the function flips between these two endpoints of the interval. So in this case, FA is less than 0, and this is FB, which is greater than 0. Okay? Then, by the intermediate value theorem, you're guaranteed that there is a point in between A and B where the function crosses the x-axis. Okay? So, how does the bisection method work now? The bisection method works by starting two endpoints between which the function flips sign. So the starting point for the bisection method is start with interval a, b, such that fa and fb are opposite in sign. Okay? In other words, this is a scenario we're talking about. Now, of course, this is not the only scenario. You could have had FA being positive and FB being negative. In fact, you could have had something even more complicated. You may have something like this, where this is A and this is B. Okay? So a function like this tells you that even though FA and FB are opposite in signs, you may actually have more than one root. In fact, you will have an odd number of roots. Okay, I'm assuming that the derivative of the root is not equal to 0. We'll get back to that point later. For now, we assume that these crossings are such that if you have FA and FB flipping in signs, then I'm arguing that the number of these crossings will be odd. Okay, so at least there will be one. Okay, so the starting point here is that you have an interval AB such that FA and FB are opposite in sign. Then all you have to do is essentially to look at the value of A plus B over 2. Okay, so this is the midpoint of the interval. So pictorially speaking, let's say this is A, this is B, this is A plus B over 2. Okay, so look at the function value at A plus B over 2. This is f of A plus B over 2. Okay? So one of two things happens. Either the sign flips between FA and f of A plus B over 2, or the sign flips between f of A plus B over 2 and FB. Okay? So depending on where the sign flips, you're guaranteed at least one root in that particular interval. In this case, you see that the sign flips between FA and f of A plus B over 2. Okay, so all I have to do is now to update my interval, specifically if sign changes between f of A and f of A plus B over 2, then update interval to A plus B over 2, else update interval to A plus B over 2, B. All right, so what have we accomplished? So this should be very familiar to you. This should start to look like binary search to you, okay? So I started by saying that my root was in this interval AB, okay? And I looked at the midpoint, and by looking at the midpoint, I figured out that the root was going to be in either the interval a plus b over 2, or a plus b over 2, b. Essentially, I have half the interval in which my root is guaranteed to be in. Okay, I keep doing this. I keep doing this until I find the solution that I'm looking for. So, of course, like I said, the first interval was between a and b. The next interval became between a and a plus b over 2. Now I take the midpoint of these two. The midpoint is here, let's say. Okay, so now you know that the function flips between these two. So now the interval becomes this. Now I take the midpoint of these two. So the midpoint of these two is right here. So now the root is between these 2 points. Take the midpoint of that. Now the root is between these 2 points. And I keep doing it until I get to the solution. Okay. So once again, like I said, this is very much like what you would do in binary search, except what we're doing here is essentially tracking a function and always making sure that over any interval the function flips sign, and I keep having the interval until I get to a solution. All right. So seems simple enough. Let's look at the rate of convergence of the bisection method. All right, so to talk of rate of convergence, I'll first define a slightly formal framework where I'll talk of convergence. So remember, in each iteration, we're starting with an interval, and we keep halving the interval down. So let's say in the kth interval, the error is ek. Okay, so I'm going to define error ek as xk minus x star. Okay, so that's the real root, and this is the root that I've found. Okay, I'm going to look at the magnitude of this. So this is the worst case error in the kth iteration. Okay, so I can also define e of k plus 1. This is x of k plus 1 minus x star. Okay, now this is, once again, x star is a real root. And the error simply says, how far are you from the real root? Okay, so ek is how far are you in the worst case from the real root. Ek plus 1 is the same thing at iteration k plus 1. Okay, so now I can start to look at ek plus 1 divided by ek to the power of p. Okay, so that's the pth power. I don't know what this is at this point. So this is the critical question that we will answer. Now, if this is equal to some constant as k becomes large, okay, so I'm looking at ek plus 1 divided by ek to the power of p. I haven't told you what p is yet. Okay, if this fraction starts to approach a constant as k becomes large, then I say that the convergence is pth order. Okay, so if p was 1, in other words, if ek plus 1 over ek, just that, p is equal to 1, is equal to some constant, then I say that's linear convergence. Okay, if p equals 2, in other words, ek plus 1 divided by ek to the power of 2 is equal to c, then I say that that's quadratic convergence. Now clearly quadratic convergence is better than linear convergence. All right, so now let's look at the rate of convergence of the bisection method. You know that at any iteration, if you go to the next iteration, the error comes down by a factor of 2. Okay, so remember, initially in the worst case I had the interval ab. Okay, how far could you have been from the solution? The farthest you could have been from the solution is approximately b minus a. Okay? The point simply being that the function could simply be this is a and this is b, and the function could have been something like this. Okay? So essentially the root is actually very infinitesimally close to a. Okay? Now the fact is the function still flips sign between a and b in this case, but the root could have been right here, and your guess would have been in, well, your guess is that it's anywhere in this range of a to b. Okay? So in the worst case, you could be essentially b approaching, something approaching b minus a away from the actual root. Okay? So now, let's say this is in iteration 1. This is n, this is interval, this is distance from root. And that's worst case. Okay? So you simply have an interval, you don't know where the root is. In fact, if you guess that the root is actually at b, the root could have been at a. So in the worst case, the distance is b minus a. Okay? So in the second iteration, let's say the interval has now become a plus b over 2. Okay? It just happened that the root is in the first half, so this is what it is. Okay? And in this case, again, now the worst case distance from the root has actually become essentially the distance between these. Okay? A and a plus b over 2. Okay? So this simply becomes b minus a over 2. Okay? So just subtract this from this, you get b minus a over 2. So you will notice that as you go through at n equals 3, you can look at what the interval is. This will become b minus a over 2 squared. Once again, it's exactly the same as binary search. The worst case distance from the root simply halves at each step. Okay? So what this tells you is that ek plus 1 over ek is always 2. Okay? So this tells you that the convergence of bisection method is linear. Okay? Specifically that, let's say you wanted b minus a over, after k iterations, 2 to the power k, and you wanted the worst case error to be less than 2 delta. You can solve this, and you'd get k is greater than or equal to log of b minus a divided by, this is log 2, this is divided by delta, and I guess there is a minus 1. Okay? Or roughly that you will need log of the interval iterations divided by delta to get the error down to delta over 2. Okay? So the important thing here is the convergence of bisection method is linear. Okay? This is not particularly a fast convergence. We will see a method soon which has convergence faster than this. Let's look at an example of how this works. Let's say I have given you an equation. Let me take an example from my notes. The equation is fx equals x cubed minus x squared minus 1. Okay? And the interval that's given to you is 0, 2. Okay? So the first thing you want to do is to make sure that the sign actually flips in that interval. So let's look at f0. f0 is, in this case, negative. In fact, it's minus 1. And f2 is positive. That's 8 minus 4 minus 1, which is 3. Okay? So you know that between 0 and 2, there must be a root because the function changes sign between these two. So we can actually work with this. Okay, so let me just go through and give you what values to get. So I'll simply I'll show you a table. The first column is simply the iteration number. Let's call it AI and BI. This is the interval. We'll look at the midpoint, xi, and finally we will look at the function value f of xi. Okay, so at iteration number 0, these values are 0, 2. Of course, the midpoint is 1, and the function at midpoint is -1. Okay, so if you simply put a 1 here, this is 1, -1, -1. So the function value here is simply -1. Okay, so now you take iteration number 1. Of course, you will notice that the root is in the second half of the interval. So AI becomes 1, BI stays 2. Okay, so the midpoint is 1.5, and the function value at midpoint is 0.125. Okay, which means that at the next iteration, AI stays the same at 1, and BI becomes 1.5. Okay, because this is negative and this is positive now. Okay, so the midpoint now is 1.25, and the function value is minus 0.609. Okay, so in the third iteration, of course, now this becomes the left end of your interval. This is 1.25, 1.5, 1.375, and the function value at midpoint is minus 0.291. And I'm going to skip a whole bunch of steps. By the time you're at step 8, your interval looks like 1.453125, 1.46875, and the midpoint is 1.460935, and the function value is minus 0.016. Okay? So you will see, you've seen essentially how this method converges to the root. All right. So this is all I wanted to talk about bisection method. There are a few notes that are important here. Let me make sure that I hit all of these notes. So the first note is that bisection method always finds a solution. Okay, so if you have an interval which flips sign, there will always be a solution between these two intervals. The next thing to note is that bisection method is a relatively slow method. The convergence rate is linear. Ideally, we'd like something that's faster than linear. And in the next two lectures, I will show you two methods, the Newton method and the secant method, which are both faster than linear. And finally, often it may happen that the intervals themselves are hard to compute, where the function flips sign. There are some optimizations that you can think of for the bisection method as well. Namely that if you know that a root is close to one end of the interval as opposed to the other. So specifically, if you know that this is A and this is B, and your function looks like this. Okay? In other words, that FA is actually close to 0 and FB is actually far from 0. Then in fact what you can do is you can do a linear interpolation between these two. In other words, that you can think of a line that you might draw between these 2 points, and you can take your next iterate to be where that line crosses the 0, as opposed to the midpoint. Okay? So once again, in simple bisection, you would simply take the midpoint of these two, but if you know that this is a lot closer to 0 than that, then you can linearly interpolate and pick that point. This would accelerate in some cases. The only problem is the proof, the convergence rate is no longer guaranteed to be linear. Okay, so you have to be aware of that, but this is a simple optimization you can think of. So that brings us to the end of our discussion on bisection methods. Thank you.